Good evening, everyone. I warmly welcome all of you for the fifth workshop of Enigma. First of all, I would like to congratulate all the winners of the mini hackathon. They have been announced last week, and also another important reminder that we will be starting the registrations for the hackathon tomorrow. So at the beginning, I'm reminding you all that the registrations for the hackathon will be open tomorrow. So I request all of you to register for that as teams. So today is the fifth workshop of Enigma, and from this workshop onwards, we aim to discuss more advanced content. So today, as you all are aware, we have an awareness session, a beginner's guide about getting to know about machine learning. So as the guest speaker for today, we have Mr. Aravind Kanchana Ruwanpatirana. He is a PhD student at the University of Utah, specializing in machine learning theory and theoretical computer science. So he completed his undergraduate studies in computer science and engineering at University of Moratuwa. And also he has served as a secretary of Mathematics Society in the year 2015. And when mentioning his achievements in 2016, he participated in the International Mathematics Competition for undergraduates and managed to earn a bronze medal. And after that, in 2018, he joined the University of Utah for his PhD, focusing on research problems in online learning and high-dimensional statistics. So currently, he is in his final semester, and he continues to contribute towards the evolving landscape of machine learning and theoretical computer science. So, Mr. Aravind Kanchan Ruwanpatirana, we are glad to have you here today as the guest speaker for our fifth workshop. So, shall we start it? Akidu, you can proceed with the rest.
Should I start? Thanks, Cindy. Let me start. Yeah, I have one quick question. Can you guys hear me?
Yes, you're audible.
Cool. Thanks. This thing. Let me quickly figure out how to hide. Hi everyone. So today we are talking about we are going to do a brief introduction about machine learning. So we'll basically talk about these like basic basic concepts, basic types of machine learning, and a couple of touch upon a little bit about machine learning theory, like a couple of theoretical concepts on learning itself, and then we'll go into certain learning models, as well as we'll sort of conclude with a with a sort of a demo using this thing called like so we'll conclude with a demo using Python, which is something you guys should be familiar with at this point. So starting off, the first question we have, like we have this thing called machine learning that has been topic of interest. I mean, for quite some time, everyone has been talking about machine learning, and the problem the problem is, what is machine learning? Even before that, what is learning? So yeah, so this is sort of a key question in understanding what machine learning is. So I assume you guys are basically familiar with this like general idea of algorithms. What is an algorithm? An algorithm is basically something, basically a well-defined set of steps to solve a specific problem. There, we basically tell whatever whoever is like. I mean, an algorithm doesn't have to be for a computer. Like, uh, so there are a lot of algorithms in mathematics, a lot of algorithms in like even in behavioral sciences. So like, it's not something that is just for like computers or anything. Algorithms just give you like, I mean, if you take for instance a recipe, that is an algorithm. So algorithm gives you a step by step guide to do something, such that you start with a set of inputs, like set of ingredients, and you end up with some yeah, some, like maybe a cake or something like that, which is your end result, which is in a way sort of in a way in a way you're guided through this thing with a step by step guide. But now the thing is, so this helps us solve a lot of problems in computing, this like approach of algorithms. But there are problems where we can't do this step by step. The enough learning comes in. Learning, simply stated, learning is this process where you interact with some sort of an environment and get information from that environment and use that information and maybe some like sometimes some reward, or like maybe like usually there is some reward in this information, or there are certain losses, like so in some certain learning process there are losses, like you might lose some points based on what you do and so on, like that. That way you try to figure out what something is by yourself. That is like the learning that is the core idea of learning. So here in this image, what you have is basically this sort of like a well, I mean, this is something we have seen in these like science books and everywhere, where they put s- pieces of cheese in a maze, and like they put mice there and they try to see how they learn to find these pieces of cheese and solve the maze. So here there is this process of there is this process of agent, environment, and reward. We'll we'll actually see this is basically this like idea of reinforcement learning. We'll sort of lightly touch upon that later as well. So moving on. So before moving on to like this machine learning, uh, I just wanted to introduce sort of like a game, and maybe briefly ask you guys like to post something on chat later on. So I hope you guys are familiar with like ICML. In there is this conference called International Conference on Machine Learning. So in 1994, at this conference, there were a couple of conferences. Yeah, at this conference, they did this thing where every registered attendee got a badge with a label, and the function that was basically used to give this label was unknown. I mean, no one knew, like, except for the guy who designed the label, no one knew what the function was. So the game that they were asked to play was to just interact with each other and try to figure out what this function was. And like one information that they were given is like the function only depended on the name. So they just had to figure out what the function was or some approximation to the function. So here are some exam like here actually like some actual people that participated in this thing and their batch labels. Can you figure out what the function is by so this is the information you have. Now you have to learn something from this information, interact with this and learn something. So from this, what like maybe do you guys have any guesses as to what the function is? Maybe if you have something, put it in the chat. Like, so in the interest of time, I'll sort of move. So basically, one thing you could see is that like so again, one thing you could see is that in at least in this specific set of samples, what are the observations that you can make? You can see that like for all the people that got it's I guess like all the people that got plus level, the second letter in their name, in their first name, is basically a vowel. Whereas for all the ones that got minus label, that's a consonant. So that's one possible function. I'm not saying that's a correct function or anything. That's one possible function. And it could be like for a different set of observations, we might have a different function. So this is basically this thing about learning. This is basically this nature of learning, where you see some information and you are asked to you see you see some input information. We in this case, which in this case are the name, and you see some either like you see some information about them that you want to learn, which in this case is labels. So sometimes it might not necessarily be there might not necessarily be a labeling kind of a thing. We will come to that later as well. So now the challenge is, can you use given this information, can you figure out what function or whatever what method was used to assign these labels or whatever information that we like whatever we want to learn to this input data. So this is the process of learning. This is basically the process of learning. You observe something and you want to match it to something, and you basically try to figure out using your observations and like using methods, how would you match these observations to like inputs to whatever outputs you want to get. And the problem is you want like this whatever you learn will depend on the sample. Whatever you learn will depend on whatever inputs you have, whatever observations you make. So learning is not something you can sort of just like come up with a deterministic it's not something where you can just come up with a deterministic algorithm and tell people to do these steps specifically. So this is where you need to think more about how you represent the problem and like how you make someone learn this thing. So before going there, so because of this, these kind of problems, I mean, these kind of problems do occur in a lot of places. Because of this, we need a way to teach computers to learn as well. Not just like, I mean, people naturally can learn with time, but the problem is computers where all we know is all we know is how to do these like algorithms in some sense. I mean, we do have these like stochastic algorithms, but at the same time, all we know is how to give something like a well-defined set of steps. So the key thing was how would we introduce this idea of learning to a computer, to a machine? So before introducing like this definition of like, I mean, there is no specific definition per se, but before introducing the definition of machine learning, uh, we'll first see like what where this is, why this is, why do we need to know machine learning, where is where does this appear right now. So I mean, so this is actually like this image is from, I think, like 2019 or something. So uh, uh, right now, to be honest, there are like so many other branches that are popping up. But the thing is, right now, if you think about it, whatever you do, like when you search on a search engine, when you search on Google, when you use Google Translator, when you use uh, when you try to figure out, like, I mean, when you I mean, not necessarily you, but like uh, even even behind these systems, like load balancing and everything, when you use certain assistants like Google Assistant, Siri, and everything, all of these things have these underlying principles of machine learning, where the machine the machine or the system basically learns and learns how to perform a specific, in most of these cases they learn how to perform a specific task. There is this whole debate of like specialized AIs versus general AIs, like uh, the gap the gap between coming up to general AI, but that is something separate. But like right now the scenario is, whatever you do, you would see machine learning everywhere. Like, I mean, you guys should know at this point, because like you guys should be familiar with at this point, because like right now there is this boom of applying these large language models, this idea of large language LLMs everywhere, like ChatGPT. People are trying to apply ChatGPT to everything. So in a couple of years, the situation will be like, whatever you do, there will be some sort of like a ML element attached to it. Like whatever you interact with, there might be some ML element attached to it. So in that sense, it's important that we understand what this machine learning is, as well as at some point we do need to understand, like especially as like maybe, I mean, not even CS graduates, especially as engineering graduates, we do need to understand how to use ML for our benefit, not just to rely on it. So, what is machine learning? The question, like now, the next question is, what is machine learning? Machine learning is sort of like this process of coming up with a computer program. So, there is this. This is a quote by this guy Tom Mitchell. He's yeah, I mean, he's a computer scientist. So there is no like, again, like I said, there is no specific clear definition of what machine learning is, but this quote does capture this idea of machine learning. A machine learning computer program is basically a program that learns from experience with respect to a specific set of a class of tasks that it tries to solve, and it also has some access to a performance measure. Like it knows how well it performs this task when it performs the task. In some sense, let's say it performs some task, it gets some feedback on how well it did, and so it tries to improve its performance, or or as it gets more experience. So the key things are, you have some task you want to learn, and you have experience in the form of, it might be some historical data. In some cases, it's just sort of like uh, a set of stream, like data that comes in a stream. You don't necessarily have historical information. Like there are these time series problems, such where you don't necessarily get any history. Like, I mean, there are these online problems actually, not necessarily time series. So then you also have some performance measure, as well as like some way you do this thing, and the performance, like in this image, if you think about it, there is this machine learning model in itself. This is basically how you would solve the problem, plus the performance measure on how you know how well you solve this problem. And basically what happens is you use these three things in conjunction to come up with a way to teach the uh, come up with a way to program this system such that it learns from the experience and improves over time. This is basically this basic idea of machine learning and the crux of machine learning. And so, yeah, so now we have seen like this idea of machine learning. Just sort of now like we are moving on to this, like what kind of machine learning, so like what types of machine learning are there, like what kinds of machine learning. So uh, to be completely honest, there are so many different types of machine learning. These are mostly like the ones I have here are mostly like the common types that you would see, learning types. But outside of these, there are lot of different, like lot of different branchings and lot of different types that are slightly different. Like so, we in this case, like the most common types that we would see are this idea of supervised learning, where there is you do learn something with an adult supervision. This is what we saw. Like going back to the this setting. This is basically what we saw in this, like in the learning of the badgers game. We have some information. We have supervision in the form of labels, and we want to learn that. Then there is this thing called unsupervised learning, where you only have information and you want to learn something on that. You don't have any supervision per se. Like you don't have any labeling or any such information you can leverage on. And then there is this thing called semi-supervised learning, which is basically in between the supervised and unsupervised learning. What you do is for some initial part you have information, but later on when you get new inputs, you need to like use for the new inputs you need to use whatever you learn and optimize on top of that. And then there is this idea of reinforcement. And basically, this is what we saw in the first slide, where you you are some sort of an agent that interacts with the environment and gets a reward. And uh, based on the reward, you decide on different actions and kind of that. So these are basically the most basic machine learning types that you should be aware of. And like the key thing you need to understand is what, like you need to understand what each of these are and where to, like when it comes to using them, where would you use them in some sense. So now delving into the specifics. So in supervised, like going into the specifics in supervised learning, what you have is basically a set of data. Like in the simplest setting, what you have is a set of data and a set of labels, and you feed them to whatever the machine you have, and then you come up with a model that that tries to learn. Given something, it tries to learn what the label of that object is. That is basically supervised learning. So the supervise in this case, the supervision comes from the labels. So for each of these things, like you are given what this is. Like you are given this, like the topmost label data point is a rectangle, and the next is a circle, and next is a hexagon, and so on like that. The data itself is labeled, so you have the supervision, someone pointing pointing out to you and telling you this is the specific thing. Now can you come up with some models like can you come up with some program that figures this out, like that figures out how to distinguish between these things. And when you give something this test data that doesn't have any labeling, can, would this program be able to figure out what the exact labeling is? So this is this idea of supervised learning. There we have a clear supervision, clear like the data itself is like in this case the data itself is telling us what we need to what we need to do in some sense, what are the things that we are looking at in some sense. So we need to use that information and try to figure out how we would come up with some program that takes whatever data that doesn't have this information and attaches that information to this data. So what kind of where is this supervised learning actually useful? There are mainly two types of supervised learning. Like I mean there are multiple types, but like two simple main types. One is classification, where the key idea of classification is where there you have a set of classes like so the simplest thing is like you have photos of digits like 0 to 9, and 0 to 9 are the classes that you have, and you want to figure out, given this photo, which class it is in. So this could be some kind of a image processing algorithm where you try to make a computer learn maybe like speed science or something like that, or it could be there could be a lot of applications on this line, but like so in this case the thing is you're basically trying to figure out a finite set of classes. So you're basically trying to group whatever you have into a finite set of well-defined classes, and this is actually used in like I said, image classification, certain diagnostic problems where like you figure out like, so in diagnostic like cancer diagnostic, given certain scans or something like that, you try to figure out, oh, given given patient reports or scans or like something like that, you try to figure out whether this patient has cancer or not. That kind of a thing where you have a well defined set of finite classes, that is a classification problem. There is this like identity fraud detection. It's again like like another simplest thing is like one of the earliest applications of this thing is like the spam detection in your emails. When you get emails, the key thing that they're doing to the thing that they're doing is basically some sort of, I mean, it's not directly classification just itself, but like there is a classification happening in figuring out whether it's a spam or not, and that uses uh, some learned models and previous data and so on. Like then there is this problem of regression where, so classification, like I said, was basically trying to map something to a discrete finite domain. Regression is a problem where you get the input data and try to map it to something that is in a continuous domain. So let me see. Yeah, something like estimating expectancy given certain parameters, where you want to say like if these were the habits of this person, they would live for like maybe 79.23 years or something like that, where you want to exactly predict something. That's where these regression problems appear. Another thing is like this stock market forecasting. There are this regression plus there is this another thing called like time series predictions. But there again, what you want to do is predict some exact value in a continuous domain. This is where regression comes in. And all of these problems, like I said, these would require Classification in this case requires a finite set of classes that are known. That gives us supervision. Like there you get some information, like maybe when you're learning, you get information on whether these specific points are in this class or not. And then in regression, you also get this like some value that you want to match. Like for each information you have some value you want to match, and you try to come up with some computer programming model that does this matching. So moving on, going to this unsupervised learning idea. Now one thing you could see is like, so coming back to supervised learning, what we had here was like in the simpler setting, what we had was a label set of labeled data. Now going to unsupervised learning, what we have is just some raw data that we don't know any, like we don't really know what these are. Now we want to maybe like, for instance, let's say we want to figure out a way to separate these into similar stuff. So we want similar things to be together and different things to be in uh, different partitions. Kind of. So this kind of a problem is an unsupervised learning problem where we don't really know what the what these labelings or whatever information that we want to get from this, but like we still know what we want to solve in some sense. We want to figure out a separation, we want to figure out something else. So there so now the goal is different. Now the goal is not necessarily to figure out something like uh, figure out this attachment of labeling or anything. It's basically just to figure out how to keep similar things together. Like in this case, it's how to figure out how to keep similar things together and separate like different things separately. And depending on the problem, it might be different. So what are the, like we saw in supervised learning, there were these common types of supervised learning: classification and regression. So are there any similar common types in this thing as well? Like one thing is this, like what you see itself. It's like one common type that you can easily see. So in unsupervised learning, also you can see that there are these two different two different key things, which is like clustering and dimensional reduction. Cluster, like the most important thing out of, I mean, for application level, like for people who are applying machine learning, I would say most interesting thing might be clustering. But for people in theory, plus like if you really want to work with data and like to learn how to handle data, then dimensional reduction is the more important thing. But like clustering is basically this idea that we saw here. We have raw data that we don't necessarily have any labeling attached to or any distinguishing indicator attached to. I mean, they have distinguishing features. Otherwise, we can't really separate them. So what you want to do is basically try to come up with a partitioning, come up with a set of clusters. So these separate things are called clusters because in some sense they are together and apart, like away from the others. And we want to make sure that similar things are together and different things stay apart. So that is the key idea of clustering. And this is used in a lot of different systems. There are these, like, I mean, there are these things called like customer segmentation systems where you you basically cluster similar customers together, and there are these there are certain recommender systems where you like this recommender systems thing is basically what you see in the YouTube and whatever, like other YouTube, or like if you use any other streaming platform or whatever, like or even Amazon or like whatever else, like e-shopping, eBay or whatever other these e-commerce platforms, as well as these video sharing platforms and whatever you use. The, the underlying idea of like this is the system that recommends you like maybe watch this thing like in YouTube, maybe they recommend maybe watch this thing, you might like this thing kind of thing. That is a recommender system, and there are certain recommender systems where what they basically do is cluster similar. When you watch something, they basically cluster. They have this cluster of similar items, similar videos or something like that, or similar items that you buy, and they basically recommend things from that cluster. That is one application, and then there are a lot of applications in marketing, customer segmentation, and so on. So that is clustering, and there is this notion of dimensional reduction where you you have data that is in very high dimension, and you want to try to figure out how to compress this data into a low dimension so that your whatever you like whatever you want to do in this low dimension gives you good enough information about whatever you would have learned from the high dimension. And uh, I, I do not uh, well, I shouldn't go that far. Like there is this the applications of this thing are mostly in conjunction with a like generally most of the applications you see of dimension reduction would be in conjunction with the other methods. Like you might do dimension reduction and then do some other thing on top of this. Like you might do dimension reduction first and then do supervised learning regression or something on top of this. So but still dimension reduction by itself is a really important thing in unsupervised learning. Then there is this idea of semi-supervised learning, where the thing is, even the so you have an input, you have a set of input data, and you have a set of labels, but your labels, they don't necessarily cover the entire class. They don't cover the entire domain. They don't cover the entire space. So you still try to come up with a model similar to in supervised learning. You still try to come up with a model that when given some unlabeled, some new information that tries to make a correct enough prediction. So this is semi-supervised learning. Right now, to be honest, semi-supervised learning is not that used because there is this like one, but still it's nice to know because there is this one other thing that I didn't include here. There is this notion of self-supervised learning, which has gained a lot of interest right now. So most people, instead of semi-supervised learning, they are turning towards these self-supervised learning based approaches. But like one place this kind of approach is used is again going back to this sort of like uh, diagnostic medical problems where you have certain re- uh, let's say X-rays or something, and you want to figure out if there is a certain carcinoma or like a certain cancer present in this scan or like CT scan or X-ray or something like that. And in such settings, there is this problem of data and labeling scarcity. Because of that, the, the people used to use a lot of semi-supervised learning methods in these cases. But with the advent of uh, with the advent of self-supervised learning and these transform models, people are moving more towards those kind of models right now. Okay. Moving forward to moving forward to reinforcement learning. Reinforcement learning is sort of like so all of these previous learning methods, while they were like, I mean, they're not really artificial in some sense, but they are sort of natural learning problems. Uh, but at the same time, if you think about human interaction kind of a setting, reinforcement learning is this in some sense, a really natural learning system where you have some person, an agent. I mean, this is like a technical term people they use, and like there is this whole notion of uh, agent-based, agent-based systems and agent-based learning models. So there is an agent. You could think of it as like some learner or a person, or like it could be just anything. So this in the agent does something, and that action that agent takes interacts makes may is some interaction with some external environment, and this from this external environment, depending on this action, you get a reward, and you do some transition based on that. Like it could be that you in this mouse in a maze case, mouse is the agent, and mouse decides to go straight, and depending on that, it goes to some point which is its new state, and it gets some reward based on whether this is like in the correct direction or something like that. So this kind of a learning paradigm is called reinforcement learning. What happens is that based on the reward each time you take a new action and you get a new reward, and these rewards keep reinforcing the way you make your actions, and this way you basically end up learning how to come up with a good action sequence. So the reason I was like, even in the first slide, the reason I included this like my example was because of this reinforcement learning. Because reinforcement learning is something you might have seen in a lot of places, especially if you're playing games. Most of these current game AIs do rely on reinforcement learning, and like, I mean, even outside of that, there are a lot of these systems that depend that basically use some form of reinforcement learning. So basically, these like real these are the sort of basic key methods of machine learning. So like depending on the problem you want to solve, let's say you want to solve a, a problem where you just want to figure out like some sort of classification or something, then you would go to supervised learning, and if you have some data that you want to partition into something, but you don't have any labeling information or something like that, you could go to clustering, and depending on what you have, you would need to make a decision on which one of these. I mean, it might not necessarily be limited to these. Which one of these things you use, and it might actually end up being that like it might be the case that you want to use like multiple of these things. You want to first do some dimensional reduction, and then do regression on top of these, and do some other stuff. So, like, depending on the problem, you might want to figure out which mix and match of these things you want to really do. Before moving, like, yeah, before going into like, so now that we have seen this, I just wanted to quickly touch upon this, like, sort of a basic theory and introduction to learnability kind of thing. So, this part is like, I mean, I am so at the time, because it's more introductory, want to introduce a lot of theory because l- sort of a deep area, and it does require a lot of ground. It does require a lot of background to understand certain, like follow certain things in this thing. So today, what I wanted to basically tell you was this how this notion of learnability came, and then I want to introduce something called pack learning, and then talk about this simple idea that is called empirical risk minimization. That's mainly it in this case. So so the thing was, machine learning has been there for quite some time. It's been there for like, I mean, I'm not even I'm not even sure where it exactly started, because this idea of regression has been like, especially this idea of regression has been there in mathematics for quite some time, and it has been in like compute, even in computing for a long time. Now the problem was, while there was this idea, there was no real way, a proper theoretical theory to reason whether you can learn something or not until like 1980s, before 1980s. So in 1984, uh, this computer scientist Leslie Valiant introduced, they submitted a paper called a theory of the learnable, where they introduced this idea of coming up with a theory to reason about learning itself. And to be completely honest, this is a theory. This theory is just a theory of supervised learning. It's not about like it's in its essence just about supervised learning. But at the same time, I just want to introduce this thing because this idea is really important, especially if you're like, if at the end of the day, if you're interested in learning about of theory behind this machine learning, ML models, and everything, like what it is, this idea itself, that this notion of learnability is really important. So before we move on to this, the definition, because the definition is sort of loaded, it does have lot of different mathematical. It has a lot of mathematics to follow. So before that, I just wanted to introduce what are the things that we have in a learning system. So we basically have a set of data, which is like some set of inputs as well as a set of labels. We also have in a learning system, in a learning, when you're given a learning problem, you also have a hypothesis, a function that maps input, like a hypothesis is just a function that maps inputs to a label. It's just some, like, it is some labeling function in some sense. You could think of it as just a labeling function. And given some data, like given inputs to this labeling function, it outputs a label. And you also have a loss function. These are so these are basically the things that we also saw in this Tom Mitchell's definition of machine learning. This loss function is this performance metric. This is a function that helps us figure out how well we did with by using this hypothesis. It's a measure to figure out whether this hypothesis is good or not. And then there is this learning algorithm that basically gets the data and tries to figure out what this hypothesis is. Like, so that learning algorithm, all it knows is the data and maybe the class of the hypothesis, and there are some other stuff like the distribution. There are some distribution assumptions depending on what you want to learn. But for now, just think of it as like something that sees the data and has access to the loss function and tries to come up with a hypothesis that gives whatever labeling that this data has. So again, a few more basics. So there is so because we have hypothesis, now there is this notion of hypothesis class. Hypothesis class is basically a class of hypothesis function. So this, in some sense, for simplicity, you could think of this as a set of hypothesis functions. Generally a set, but there are these like set rules. Just think set of hypothesis function, and we usually use this like curly h for this thing, curly h for hypothesis classes, and any hypothesis we use is in this hypothesis class. And so one simple example of hypothesis class is basically all possible lines or something like that. All possible lines that go through zero. That's a hypothesis class. And any specific line we use is in this hypothesis class. So it's that kind of a thing. It's well defined. It doesn't have to be finite. Again, like I said, if I pick this class of all, like if I pick this set of all possible lines that goes through zero, that's not finite. There are like infinitely many class. Pick between any 2 points. So there are infinitely many lines that go that that are like basically okay, that goes zero, and that lies between the arc between those 2 points. And as long as those 2 points are not collinear with zero. Okay. So again, coming back to there is this notion of there is another idea that input to formally define these things, we also need this idea that inputs are coming from some domain. So in this case, you could think of it as like a non-domain as well. And inputs are sampled from this domain based on some distribution. The domain has been, I mean, generally there are cases where you don't even have access to the domain, but like generally the domain itself is. And the point whatever D is not known to us. So given these elements, there is this notion of two different notions of error. Error, and you somehow came up some hypothesis for this thing. Generally, basically, for generalization in expectation, as come from this distribution in expectation, how much of a loss would we suffer? Something license an array is something that's defined on the distribution that depend on the entire. But the problem with this is not something we calculate because we only have a small set of samples. We don't know, like, so if you really want to this is basically the probability or the expectation is over the x over this distribution. We do need to know the distribution D. But the problem is we do not distribution D. So how would we do this? There is no way we can do this. So because of this, people introduce this idea of empirical risk or empirical error or like model error. People call it different names. Empirical risk is this idea rather than looking into this like unknown distribution, rather than trying to look into this unknown distribution, you basically just take a set of samples and you calculate how much error you get from each of these observations in the sample and try to figure out what is this sample mean the what is the sample mean error what the sample mean loss is. So these are the two key things. So now what I'm trying to like what I will do first is introduce and then introduce empirical risk minimization. So pack, the main reason I introduced backlining is not necessarily because it's important for content that follows. It's not that important for the most. It's just because it does give you this notion of how would you figure out something is learnable, and also I usually have a question. I see a raised hand. Do you have a question? Please feel free to like use chat or like even yeah. If you have any questions, please feel free to put it on the chat or like even if yourself. That's fine. But like the chat might be easier. Moving on. So mm, when we need this idea of realizability assumption. Realizability assumption simply says that there exists in our hypothesis class, whatever we pick, there is a hypothesis that does exactly the same thing the function does. The function itself is, I mean, it might not necessarily say the function itself is in, but it is saying there is some hypothesis the same thing as the function does. That is like gives zero loss over distribution. So that's just something that that is needed for pack learning, but so is basically something that is actually like the is about a very specific class of learning. It's talking about this idea of probably approximately correct learning. You're not trying to learn. So again, unpacking this, in this case, you're not actually trying to learn things exactly. You're trying to things approximately, learn something approximately correctly. And again, that also with some probability. There is a probability that you might not actually learn this, and there is a probability there is a probability that you might not get this get this approximately close bounds that you want to do, and so on like that. So this is a very restricted setting where you only try to do something stochastically, like with some probability, and you still want to approximately correctly do something. So pack learning is defined on hypothesis class, and what pack learning tells is uh, so the statement of pack learning is slightly complicated. I mean, slightly involved. It's basically here what it is saying is for any hypothesis class, you can define a function. This is a sampling function that takes this epsilon and delta. Epsilon is basically the error that you want to achieve, and delta is this probability. I would say delta is the failure probability, and that takes these inputs and with some samples you would need, such that if you had this many samples, like if you had more than that number of samples that are independent and identically distributed, gen- taken from the distribution D, and if you label them by your labeling function, then this for this hypothesis class to be pack learnable, this class there should be an algorithm that returns a hypothesis such that will be at least like 1 minus delta. That is like with failure probability, that is success probability minus. You get a generalization error that is like you get something that is epsilon close to, like you get a hypothesis that is epsilon close to your function based on your loss. So this is a lot to unpack. I get, but what in essence what it is saying is that there is some finite like there is some finite number where like if you sample more than that number of like for any so for any epsilon instance. So like for any epsilon and delta, there is a finite number. If you sample more samples than that number, if hypothesis class is backlearnable, you should be able to figure out a hypothesis that is epsilon close to the true labeling function, which means like if you have enough samples, you basically end up learning a good enough labeling function, good enough function that learns whatever you want to learn. And depending on this epsilon, epsilon, picking epsilon, com- picking epsilon carefully, it basically tells you that like as long as you do this, you have a good enough learner, and like this should be able to do what you want to do, and you don't need to go into more examples and trying to find like trying to do aggregated learning or something like that. So this is basically this idea of backlearnability and backlearning. So now they just to introduce the idea of learnability and like just to introduce this idea that like as long as you have enough samples. So this highlights this key thing in learning, the fact that you do need sufficiently, like if you want to learn something, you do need to see sufficiently enough samples that so that you see the desired information. Again, this version of pack learning is this like the simple pack learning. There are a lot of different like there are different versions of this thing as well. Like there is this thing called agnostic pack learning where so here there is this assumption that you had this realizability assumption that there was something that gave zero error. So there are there are so many other like there is this notion of agnostic pack learning where we even remove that, and we even where we basically even remove that constraint, and we don't even need realizability, but that basically introduces other error terms. But like we won't go into that anyway. So now moving on, I just wanted to introduce this idea of empirical risk minimization. And empirical risk minimization is a very simple idea. And this is in some sense one of the simplest learning algorithms that you can think of. So the idea is given a set of sample sets, you basically try to go over all the hypotheses, and try to figure out which which hypothesis in this class minimizes this uh, minimizes our empirical risk. So that's all you do. It is a very simple thing. And so the hope is that this would give a hypothesis that is close to the hypothesis that minimizes the generalization error. The problem is whether you succeed in this depend on the amount of data you have, how complex the distribution is. Like when you have a complex distribution or skewed distributions, if you don't see certain stuff, you might not necessarily learn some information. And then it depends on how complex the loss function is. For certain loss functions, it's easy to do this kind of empirical risk minimization. But like for certain loss functions, do need to do lot more work. And it also depends on what the true underlying learning function is, like the structure of any function, whether it's linear or if it's periodic. Like again, it depends on certain properties of this loss function, whether it's convex, whether it's smooth functions and so on like that. And yeah, just to touch up, yeah, let me quickly go back to the empirical risk. So all we are doing is coming up with a hypothesis that mean loss we have, like the uh, sample mean of the loss we have. That's all we are doing. And it turns out in most cases it is like, I mean, technically when it is possible, it does well. Like technically in most cases when it is possible, there are cases, there are proofs that tells us it does well enough. Co- While it is simple, it does give you a very strong learning algorithm. So as keeping this as a starting, so at the same time, one other thing I want to say was depending on these parameters, as like depending on these some of these parameters, this could be a problem that is hard to solve. So it's not a for all solution. It's not a general solution. It's just a start that you can take. Like when you want to learn something, this is a start that you can take as long as you have access to. You can just search the entire space if possible. Like especially if it's finite, you can do that and try to figure out something that minimizes the error for the samples. So now now I'll just sort of quickly go a little bit more details into supervised learning just to introduce different uh, types, like a few different supervised learning methods, as well as then to go over like how they relate to, especially this empirical risk minimization. So we'll start off with linear predictors. So this is not necessarily supervised learning per se. Linear predictors are basically just sort of a key idea that is used in a lot of supervised learning methods, especially linear supervised learning. So a linear predictor, what it does, so uh, introducing a linear predictor basically before uh, to introduce a linear predictor, you do need to introduce this idea of how, like, I mean, so one thing, I'm assuming you guys are familiar with dot product and these linear mappings and stuff like that. So what linear predictors are basically doing is given some given, so basically this is basically given some x. This is a mapping. A linear predictor is a mapping. This is a function. Linear predictor. This is a class of set of linear predictors, I guess. And an element in this linear predictor is a function that takes x and maps it into uh, some so these x's are vectors, by the way. Takes some vector and maps it into the real space using this like W transpose X, which is basically it does some dot product or dot product using some set of weights. This is basically, you could think of it as like, assume X is something like X1, X2. The idea is this basically. So the idea is this basically, given. uh, So yeah, just in case if you guys are not familiar, this is basically assuming X was something that is like X1, a vector that is X1, X2 up to some Xn. W for X is basically something like sum of Wi Xi, which is I going from 1 to n kind, where you basically multiply corresponding items together and add them up. So, so this is the basic notion behind linear predictors. They're just they are just a set of like a class of mappings from one, like, that takes some vector as an input, the dimensional vector as an input, and outputs does a linear transformation on top of those and outputs some real number. And usually these are defined on the definition, the dimension. This d is the dimension of x as well as w. And the thing linear predictors does for us is, with linear predictors we can introduce the idea of half spaces and learning problems that use half spaces and linear predictors. So the idea of half spaces is a simple idea. So okay, how do I delete these annotations? Okay. Okay. So the idea of half spaces is really simple. What you basically do with half spaces is you pick some linear linear predictor. You pick some linear predictor in something, in the simplest setting. If you would think of this as some plane, or like, I mean, generally some kind of that plane, or like, in the simplest setting you would think of it as a line. You pick the line and you basically divide the space into two parts. Top, like, the top section of this plane is positive part and the bottom section is negative part. Formally what you have is this, like, uh, half space of dimension d is basically applying a sine function over, like, applying a sine function over the class of functions uh, in linear predictors of dimension d. So basically when you when you substitute an x to this thing, if you get a positive value, then you are in the positive side of the half space. Like, you are in the positive side of the plane, or otherwise you are in the negative side of the. Now, why is this interesting? The reason this is interesting is because what you can see is this is basically doing a separation of two things, which is basically this idea of classification in some sense. Like, if you had this, like, plus one minus one labels or zero one labels, or something, like, if you wanted to separate two things, what you can do is, as assuming these things are linear in some, like, they have some linear relationship, you could just try to figure out this half space that separates them, and you have a nice separation. And whenever you get new things, you can just, based on where it is with respect to this half space, you can figure out uh, how to label them. So this is where half space come in. With this in hand, we can actually introduce this idea of this. I mean, really, this is an algorithm that you can actually use in um, in some sense in binary clustering, binary classification. Technically, there are these other versions of this thing that you can use in some high dimensional settings, but the, like, high multi-class settings. But this is basically just for binary classification, and this is basically a simple algorithm called perceptron. And in some sense, this is just all this is doing is doing empirical risk minimization. And uh, so the idea is simple. You are given a set of samples that is in the form of x, which is the input, and y, which is the label. And you want to figure out a vector w such that the sign, like, the sign basically means this plus or minus of this. Like, in some sense, you could think of the label as plus, like, I mean, plus or minus. And you want to figure out a vector W such that this uh, the linear predictor you get from W is the correct half plane, correct correct half space that gives you this labeling. And the key thing you can observe is that assuming assuming this is correct, then when the sign of yi, like when yi is like assuming w was the correct one, when yi was when yi is plus, w times yeah, the inner product of w and xi has to be positive, which means yi times this w xi has to be positive. And the nice thing is, even when it is like when yi is negative, this relationship still holds because both of like if they are correct, both of them have to be negative. Now, what this perceptron algorithm cleverly does is that whenever it sees data or any data point, whenever you see something that is less than or equal to zero, which is basically telling you that the labeling and whatever you get from W doesn't agree, you modify your W. And so basically, in some sense, what you can see is that you only do a modification whenever there is a potential error. And this is basically just like this is basically a simple algorithm that just uses this idea of empirical risk minimization where you use the where you use these samples and try to figure out something using the samples, like basically something that minimizes the error on the sample. And it turns out this though this algorithm is simple, this is just a direct sort of a simple implementation of the ideas of ERM. This does have a nice sort of a error bound in something. So what we can show is that assuming you have this, so what you can show is that the error of this perceptron algorithm basically relies on how large your xis are, as well as how like uh, basically this idea there is this notion of separable, like the notion of how separable the points are, which is captured by this b, which is telling us like what is the smallest w such that this instead of yi and w xi being 0, what is the smallest w we can pick such that we get something that is greater than equal to 1, that is like, so that is basically far from the midpoint kind of thing. So you don't actually get something really close. Essentially what you're trying to figure out is a W such that you have a sufficiently large gap. So basically a W that guarantees separability. So it's basically trying to figure out such minimum such W, and then then the other thing is how large your xis are. So depending on those two things, apparently what turns out to be the case is like depending on those two things, you can figure out how quickly this perceptron algorithm would actually give you correct solution. And in most cases, this we saw a very simple algorithm of very simple algorithm of separation, and Oh, like so here what we tried to see was basically we saw this idea of empirical risk minimization, and I wanted to really like this can be actually this is actually applicable in real situations, and this you can use. There are algorithms that are basically developed on top of on this idea. Now we have seen this. Like we want to move on to relatively more interesting stuff, I guess. So now that we have seen perceptron, like and everything, we now sort of quickly switch to something else, which is linear regression. This is like one of the simplest forms of regression you can think of, where the idea is to basically learn, I guess, learn a linear predictor, and the hypothesis class you search through is the linear predictors, and you're trying to figure out, like, given some set of labels and data, you're trying to figure out a hypothesis in this class of linear predictors such that your you guys this in this we look at the mean squared error, that is basically like uh, you basically look at some example of it, and this is basically in some sense place, and I mean this is risk. What you can see is this is just empirical risk, and what you do is find the w that minimizes this empirical risk, and which is just empirical risk minimization. So linear regression is empirical risk minimization with the hypothesis class being linear predictors. That's basically the key thing. And so the nice thing about linear regression is, so if you think about this, now we don't know how, like, at the get-go we might not know, like there is no information from this like that tells us how to do this easily, but the nice thing is it turns out this you can actually do computationally, in like computationally in the sense like you can actually algorithmically do this, and the reason for that is because everything is linear, and so the reason for that goes to, I guess, calculus as well as the linearity of these functions. Be- so the thing is, when we at this point where this thing is minimized, what you have is a function with gradient. At this point, thing that turns out to be becomes linear. The gradient itself, the functions you have become linear, and they use linear algebra to figure out you from this information. So, like I said, so if we just consider the gradient of the function, we get this as the gradient, and we want this to be zero when this is maximized. And it turns out basically this maximization, the solving and trying to figure out W star, is the same as trying to figure out W star given a matrix A defined as the sum of I equals sum over the samples xi transpose. This is called covariance matrix. And then another vector that is sort of like a sum sum of xi's scaled by the labels. And as long as the matrix A is non-singular, you can actually calculate this directly. Even if it is singular, there are methods. So as long as matrix A is non-singular, you can solve linear regression. Uh, you can actually solve linear regression exactly in the sense, like exactly algebraically, analytically. You don't even need to like come up with a computing program. You just like so all your program would do is calculate this A, and the inverse of A and just take A inverse C. And that your W star and whatever new inputs get, you basically take the product of W star and the new input. So these basically telling us that learning linear regression is really easy, but it does depend on this covariate matrix being non-singular. Assuming we get a singular covariant matrix, there are tricks you can do. There is this notion of Moore-Penrose pseudo inverse, where instead of trying to do like the reason you can't use this for singular matrices is because the inverse is not defined. What Moore-Penrose pseudo inverse does is to define a notion similar to inverse for such matrices. But then again, there are conditions on top of that as well. There is this, and there is another notion of like there is another notion of principal component regression. So this is the reason earlier when I was talking about dimensional reduction, I was saying in certain cases you might want to use dimensional reduction as a precursor to something else. So there, what we are doing is basically using dimensional reduction to reduce the dimensions so that whatever data points that you have, they are sort of they are somewhat independent, and then use linear regression or whatever regression you want on top of that. So uh, as long as you know these specific parts, linear regression, dimensional reduction, and you can you can sort of mix them together and try to figure out how to use them efficiently so that you would get what you want. So the next thing I want to quickly go over was logistic regression. So while this is called regression, this is more of a classification problem. So to understand, to define logistic regression, we first need to introduce this idea of like sigmoid function. Sigmoid function is a function that basically, it's basically this like green function which oscillates between like which oscillates between 0 and 1. Yeah, it oscillates between 0 and 1. It's in some sense, well, there is some sort of a skew symmetry kind of thing. And this, like, one nice thing this does is using this, as you can see, like, so if you look at this thing, like, after some point, whatever you get from the sigmoid function is close to 1, whereas uh, before that point, before this like point of 0, whatever you get from the logistic sigmoid function, logistic function, is close to 0. And this is basically giving you a way to separate whatever, like separate your inputs into two different classes, like 1 being one class and 0 being the next class. And like, yeah, I mean, here the only key thing is like at 0 you're exactly at 0.5. And what logistic regression does is to basically use this idea and basically take try to look at the hypothesis class, which is basically taking this linear predictors and applying sigmoid function on top of this. And in this case, what we do, like, I mean, in this case, you usually use a different log. So different loss function, there is like logistic loss, like log loss functions. And then uh, again, what you want to do is empirical minimization. But but the thing is, this is not like so. One thing we saw in the earlier case was this was sort of straightforward. Now what we have here is not really some like, a straightforward calculation that we can do. So in such cases, we do certain uh, we come up with certain algorithms that solve these things. I won't go into specific details of the algorithm because I just wanted to cover these like, ideas of these problems as well as like how they relate to these theoretical concepts. So one good one thing is in this logistics because usually what people do is on top of this they once you do regression and get some value on top of this what they do is they do some sort of thresholding on this value and figure like converting it to a classification problem. So like if it's greater than 0.5 you assign label 1 and if it's less than 0.5 you assign label 0 kind of. Technically there are a lot of things you can do on top of this kind of thing, but in general this is more of classification, the sigmoid function and this comparison. So yeah, so there are a couple of other stuff that I want to introduce that are like more related to classification. I guess like the first thing is decision trees, where so a decision tree is a very simple idea. One of the simplest forms of learning models where you have you have a tree where each these these are your like feature has node and you start with some how how you select these features and like the ordering of the features and everything depends on certain like parameters such as like there are these uh, end end of stuff and there are algorithms. There is this algorithm called ID3 and a lot of different algorithms that actually come up with show you how to come up with these things, but we won't go into them because that does involve a lot of other discussions. And so uh, all I want to tell you is this idea of decision trees, which is like a very simple thing. And these you might actually see these kind of stuff if you try to implement certain things. There are these boosted decision trees and like especially when you're doing boosting kind of stuff, there are these things coming into play. And in addition to what you have is basically just a tree graph where each edge you take is some decision and uh, each basically a feature or in some sense a state kind of thing, a feature. And at that like depending on that feature, you 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 start with the root node and make a decision based on your current value for that feature. And you basically try to make decisions until you reach a leaf node. And the leaf nodes basically give you this uh, class that you are in once you do this classification. In this example, it's basically the risk of heart failure. And based on that, like if you are if your age is less than 18 and if you're less than like 60 kilos, you're low risk and so on like that. If you're older than 30 and if you're not a smoker, then you might be low risk. That kind of stuff. Like so how you design these kind of things depend on other parameters, but there are so this is just a simple notion and then so this is this notion of decision trees, but then like as soon as you have trees, there are like so if you guys are familiar with algorithms, you might know, especially like as soon as you introduce this notion of trees, you also introduce this notion of forests and everything. Similar to that, there are like things built up on top of these things, like such as random forests and so. But those are something for like a separate day, I guess. So going forward, one other thing I wanted to introduce was this idea of k nearest neighbors. K nearest neighbors is again like a very simple, I mean, supervised learning algorithm where you basically have what happens in this case is you have a set of labeled data in two different classes. Here, let's say just two different multiple classes. Wait a minute. In this case, you look at multiple closest neighbors. This is like you're looking at the five closest neighbors and figure out what are the labels of these neighbors and pick the majority label. So in this case, you see the new data point, you look at the five closest neighbors, and you see you have label A three times and label B two times, and you would end up labeling the new guy label A. And in some sense, this is a very simple algorithm as long as you have some label data, and as long as you're doing a classification task, you can just do this rather like can implement this rather easily. While this is simple, this is actually like a really useful algorithm, especially if you're doing classification in like in a simple setting. So this is it for like supervised learning. I'm moving to unsupervised learning. I just want to introduce this idea of clustering and dimensional reduction, like clustering more in like general sense, and then the idea of dimensional reduction and one specific thing called like principal component analysis. So the idea of clustering is a very simple idea. What you all you're doing is you have a set of unlabeled data, and you you run some algorithm on top of this and try to figure out a set of clusters such that each cluster is sort of like a partition by themselves. And this problem is really useful when you have when you want to, again, like you said, like when you want to figure out like in practical applications. So one place where this was actually used was this. Uh, I mean, I'm assuming most of you are familiar, like, I'm assuming most of you are familiar with Yahoo. Like, so in Yahoo, they had this Yahoo News platform, and what they were basically doing was to do recommend like when you in order to recommend news articles, what they basically did was to do this kind of a clustering on top of news articles and figure out partitions of news article. And when you see some news article, they basically recommend something similar from those clusters. And so the methods themselves, there are so like depending on the problem that you want to do, there are so many different methods. So in something you might have heard of, but there are, I mean, you need to name depending on the problem, depending on the situation. There are too many to be named that you can use. So, like few examples are like there are these things called spectral clustering, there are DB scan methods, and then there are these specific. Uh, I mean, even in K clustering methods, there are K center, K mediate clustering, and a lot of different methods that are coming into play. But the key idea behind them is you have some unlabeled data that you want to separate into partitions. So it's how you would figure out this partition. So now moving on to dimensional reduction. So the idea of dimensional reduction is really simple. You have data in a very high dimension. What you want to do is to like, let's say this is just three dimensions. It could be like, I mean, in reality, it could be actually like 100 dimensions or like even more than that. And to this, to a low dimensional representation, maybe 2D or 1D. But you don't want to, like, the thing is, you don't necessarily low dimensional representation that loses information. You want to go to a low dimensional representation, preserves as much information as possible. So this is the key idea of dimension reduction. There are so many methods that does this thing. Like there is, depending on the problem, there is principal component regression. You could do singularity compositions as well as like independent component analysis, and there are these things MDS, and so like I mean there are so many different methods and so many depending on the application, so many different things you could do. But generally, in this specific case, we'll quickly look at this idea of principal component analysis. So principal component analysis, in my opinion, like the one of the most important ideas in dimension reduction. What you basically do is you have data in high dimensions. Here we have used 2D, but like technically it's in high dimensions. And what you do is to figure out, so these are correlated data. So like these data points have some correlations in these dimensions. What you want to figure out is how would you go from this to a low dimensional data representation where data points are not related. Like here, points might be like they are correlated data points that are linear and so on. So the idea is very simple. What you end up doing is basically taking this set of data points. You basically like you try to center this data set. You try to figure out the center of the data points and move your axis to that point, and then try to figure out on this like centered data what are the key directions. What directions are the variance minimized? And to getting this figure these things you can do by covariance metrics that we talked about in calculus of those covariance metrics. Using that, you basically end up getting this low dimensional representation where the data points are uncorrelated, so that you can then use those information to do whatever you want, maybe regression or some other thing. So this is basically this idea of PCA. So we have, I guess now we have come to the sort of the end of everything, almost to the end. There was one other thing I wanted to do. So I just maybe I can like, how much time do we have? So yeah, let me open this thing. Yeah. Okay. So if time, I'll quickly do this. So let me quickly connect. I'll actually share this with you guys, so like you can actually try this out. Uh, Technically, these are not my codes. I also took it from some resource that we use. So Let me quickly get the data. Let's quickly look at how you would actually do linear regression in a real setting. So first of all, like here I'm using Jupyter notebooks, and actually I'm using Google Colab, which is a free tool that you can use, and using Python and Jupyter notebooks, which is like usually when you do these kind of things, at least in development phases, you can actually use these things because it's very fast and rather interactive. So here I'm like what we do is we initially import some modules, which is like these are the key modules that we import are like NumPy, Pandas. NumPy is basically something that gives you tools to do numerical calculations on like like on matrices and stuff like that in like on this gives you a lot of tools to do linear algebra, and then you got pandas, which is a tool that gives you uh, which is a module that gives you tools to handle data, and matpl like matplotlib and seaborn are both just tools that gives you uh, modules that gives you tools to do plotting and related visualizations. So generally you need some computational modules, some uh, some modules to handle data, and some modules to do visualization, because these are key parts. And then I mean, so this also like this might include certain other stuff like scikit-learn uh, and some other modules that depending on the situation you might want to do TensorFlow and so on. So we start with reading the data. It's like it's a CS housing prices in US. It's loaded. Yeah. So this uh, pandas gives us this read CSV file that helps us read. I mean, technically not even CSV files, anything comma separated, it'll automatically read, and even if it's not, you can define certain parameters. And I'm not sure what it's taking to. Anyway, one second. Let me quickly go. There seems to be something wrong uh, with the runtime. I'm not sure. I'll just go information I have from the previous one. Once you have a data frame, you can use dataframe.info to like, okay. So what this df, what this does is to read this information to this thing called pandas data frame. And from there you can check the information about the data frame and figure out certain statistics. Okay. Yeah, it seems like my browser decided to pick this time to update itself. Yeah, yeah. Let me quickly once I get this loaded. Let me try to write this. So you guys can access like the link should be working. It's it's this. The problem is it's a problem in the local browser. Like so, Google Collabs needs local browsers permission to run certain JavaScripts to display certain things, and because of update, the browser because of update that happened while the presentation was going on, the browser is blocking Collabs from displaying anything. Anyway, you guys can try. By the way, I'll share the presentation with you guys as well, and you guys can try using try this with the link as well. And they have this step-by-step guide to how you can use step-by-step guide to how you can come up with a Mhm. Maybe I won't run this so basically uh, so I have results from my previous run, so I'll quickly use that. So you can use once you load the data frame using this, you can use like info method to check the types and everything, and describe method to get information on like statistical information on certain properties, and then try to figure out what the columns are. All of this is in the collab file itself. And then, I mean, the pair plots thing is not really that important, but the thing is basically you usually use this idea of pair plots to figure out certain correlations between specific features. So this is basically like what this does is to plot the correlation between all features pairwise as pairwise information. And then this other thing is basically the distribution. And then you can, again, this is not that important. Let me quickly go to the actual regression part. So let's quickly go to starting the actual regression part. Oh yeah, yeah. So when you're doing regression, what you want to first figure out is what is your input data and what are your output data. So what we are doing here is basically telling our system we want this set of columns from 0 to like last 0 to some column number as our input data, and some column number like some column as our output data. And you can use pandas data frames to basically separate these things rather very easily. And given this, yeah, like so here, I mean, this dot shape is actually something that comes from like NumPy, where what this tells you is you have 5,000 data points and you have five features, and here you have like 5,000 different labels. So then what you generally do is, so here we use this thing called scikit-learn, sklearn, and from model selection we take this thing called train test split, which gives you a set of training data and set of test data. And once you have training and test data, all you have to do is like use whatever tools you have and figure out how you would learn, and then try to figure out how well did this do. So for this thing, so the nice thing is like if you just pick sklearn or something like that, depending on what you want to do, if you pick, there are so many Python modules that actually gives you all the tools you want to do to learn these, like do linear regression, logistic regression, or any simple model. And here all we are doing is basically defining a linear regression object and trying to fit the training and test data and trying to come up with a linear regression that fits this training and test, like training data, only training data. And that, so that like, so the nice thing about these things is they internally do all the calculations, and then they basically give you what these models like, what are the coefficients, what is W and what is B in some. And like, using this, you can basically now that you have training and test data, you can basically look at the what are the errors in this. You can, how well does this, you can try to do this thing called R squared error, like root mean squared error. And then you can also try to, now that you have this thing, you can try to make predictions on other things. Like, so now we have this class of predictions and all like, so now we have the test set, and what we can do is basically try to use our model, use the predictions. Let me try to use our model and do predictions. Where are the predictions? Oh yeah. So I mean, so basically once you have a linear regression model, you have this predict term. As long as you give some input, it gives you the predictions. Somewhere, but anyway. Oh yeah, here you're doing. We take the prediction and we try to see how, like, how well this does this model does. How well does this model do against the real values and so on. Like that. So this is the key idea behind the key, like this is sort of like uh, sort of a way you can do regression when you're doing you're doing machine learning practically. So the key thing is basically, as long as you have certain modules to load these things, if you use Python or like most of these statistical languages, Python are, they all give you tools to solve all of these things rather efficiently. So one thing I would recommend. Oh, sorry, oh, I didn't see. So okay, it seems like I might have been on the slide. So okay, key takeaway is that like I will share this link with you. Like key takeaway is that Python, like these tools give you like Python and these Jupyter notebooks and everything gives you a way to like tools such as like like scikit-learn and like yeah scikit-learn and different modules that gives you a way to actually solve these things rather than without having to like de design models from bottom up. So thing you should do is actually like maybe try to start thinking about simple problems that where you can use machine learning and try to see how you can actually approach these kind of problems and maybe use these kind of things and try to see what you can actually do in this domain and start learning early. I'll stop the presentation here and I can, uh, yeah, I can try to answer the questions. So spam prediction, yeah, there is a question on like training a model to for spam prediction. So usually, so in general, in spam prediction, what like uh, to be completely honest, right now spam prediction is sort of like uh, much more com complex because you can like you can even right now with this, especially with the advances in NLP, spam prediction is in a much more advanced state. But generally, what spam prediction uses as data is the words in the email. And also, right now, they do use the context in the email as well. And then what they basically do is they they usually most of these spam predictors they have a set of emails that are recognized as spam, and then like they also have these general emails that are non-spam, and then they train a classifier to uh, to basically do this binary classification spam and not spam kind of thing. So that's like in the most simplest setting. Right now, to be completely honest, most of these things are sort of there are a lot of underlying uh, NLP going on with this spam uh, classification as well. Because if you think about it, like if you just rely on words or something like that, it might not necessarily like you might end up marking certain things as spam just because of certain words like price or something like that. That uh, because of simple trigger words. So you do need these classifiers right now to be context aware. So in some sense, you could think of like right now if you're trying to build like at this moment if you're trying to build a spam classifier, what I would recommend is to uh, come up with a set of features. Like you still need these like key terms as well as a set of features that are sort of dependent on context. Like you do need some way to track the context as well. So that kind of any other questions in general? If there are no more questions, I'll hand it over to the organizing committee.
Yes.
Thanks, guys.
Session. So on behalf of Moramex, I would like to express my gratitude for dedicating your time and effort to conducting this session. And as a final reminder, I would like to remind all the participants that we will open the registrations for the hackathons tomorrow. So please do
Okay, sir,
register as
about your
team.
question, I can share a book with you. There is this book by Ben Shalev that. Sorry for interrupting. Yeah. I have this. I can share this book with you. Like there is this book by Ben Shalev. So that talks. Since I've shared the screen, understand. There is this book called Understanding Machine Learning. This book. Uh, so you can. It's. I mean, it's technically available on Amazon, but like it's freely available on the author's page. I'll share the link. And so this is the book. Uh, it's called Understanding Machine Learning from Theory to Algorithms. It talks about this entire area of like learnability, how you formally define algorithms and how you actually come up with learning like theoretical guarantees for these algorithms. You can yeah, share the link with uh, I'll share the link with you guys as with the organizing committee later, so you can share it with anyone who is interested. Sorry.
We will share that in the group, and also few people have requested for recordings if available. So the recordings of this session will also be shared in YouTube. So then, thank you everyone for joining. We can conclude the session now.